Space is a cold, dark abyss, permeated by lethal radiation where no life can survive. At the same time, a great number of fascinating objects are scattered across its boundless expanses, which can't but amaze. These are not only bright stars, but also a great diversity of most unusual and mysterious planets, from small rocky mini-Earths to tremendous gas giants. Today, we invite you on a virtual journey to some of them. First, we will visit the system closest to the Sun, known as Alpha Centauri. Then we'll fly past the mysterious super-Earth Teegarden b, which boasts the highest Earth similarity index. After that, we'll make acquaintance with the stars closest to our Sun. On getting far into the depths of the universe, we will enter the atmosphere of a gas giant and see an extremely rare system made up of two brown dwarfs. And then we'll take a fantastic virtual tour to remote galaxies at the very edge of the visible universe. Let's get ready, and we begin. Cosmo. The first in outer space. The Earth has been emitting structured radio signals into space for around 100 years now. The radio noise from the Earth reached dozens of other stellar systems long ago, including Arcturus, lying 37 light-years away from us, and Aldebaran, which is roughly 65 light-years away. Besides, our radio signals may be heard on the surfaces of a great number of potentially habitable exoplanets, like Ross 128b or Gliese 667cc. Still, the triple stellar system of Alpha Centauri remains the closest neighbor of the Sun, which automatically makes it the first obvious candidate for the destination of the first ever interstellar flight. Alpha Centauri is known to be a multiple stellar system made up of three components. Two of the larger ones are relatively close to each other. Seen with the naked eye, they appear to be a single source of light. The two components follow a slightly elongated orbit around the common mass center, which takes around 80 years to complete. The maximal distance between the stars may reach 35 astronomical units, with the minimal distance reaching 11.2 astronomical units. As for the distance between these objects and the Sun, it is reportedly 4.36 light-years. The most massive, the largest and the brightest component in the system is dubbed Alpha Centauri A. This is a main sequence star with a mass of about 108% that of the Sun. Its radius is reportedly 1.22 times that of our Sun. Even though the surface temperature and the spectral class of Alpha Centauri A are close to those of our star, it emits 1.5 times as much energy. There are no confirmed exoplanets in the environs of this star. However, while the star was being observed in the infrared in 2021, some evidence was found of there being a planet-like object close by. According to preliminary estimates, its mass may be anything from 9 to 35 Earth masses, and its radius may measure 3.3 to 7 times that of our planet. 1.1 astronomical units away from its parent star, the hypothetical celestial body completes a full orbit around it within roughly a year. Additional observations are called for to verify the data, which can be done with the help of either the James Webb telescope or else Earth-based observatories. The second component of the system is called Alpha Centauri b, or Ptolemy, and it also falls into the class of main sequence stars. However, its mass is 10% less than that of the Sun, and its radius measures only 86% or so that of the Sun. Ptolemy is also slightly cooler than our star. Its surface temperature is reportedly 5,260 Kelvin, or slightly lower than 5,000 degrees Celsius. With these factors combined, the celestial object has an orange hue, and its luminosity is on average twice as low as that of our Sun. Incidentally, Alpha Centauri b emits a lot more energy in the X-ray range compared with other objects of its class. Besides, the star is peculiar for its temper, and there are bright flares and ejections to be seen on its surface. No confirmed exoplanets have been detected near this star either. In 2012, a group of astronomers from the Geneva Observatory put forward a suggestion that there was a planet very close to it, whose orbital period was around 12 days and whose radius measured slightly less than that of the Earth. The suggestion was made based on 4 years of observation of the star's proper motion. However, 3 years later, a mathematical error was detected to have been made in the course of data processing, and so the idea of there being a planet was found to be erroneous. The third component of the system is a stark contrast to the first two. It is a red dwarf with a mass approximately 12% that of the Sun. Its size is about 7 times smaller than that of the Sun. Its surface temperature is only slightly higher than 3000 Kelvin, and its luminosity is just a measly 0.17% that of the Sun. Of all the components of the Alpha Centauri system, it is this dim space object that is the closest one to the Sun, lying 4.25 light-years away from it. This is what earned it its name, Proxima Centauri, which is Latin for closest. Besides, the object is getting nearer and nearer. Thus, in 26,700 years, it will be only a bit more than 3 light-years away. Still, this star cannot be seen from the Earth on account of its low luminosity. Proxima is noticeably far from its two companions in the stellar system. This distance is currently around 13,000 astronomical units or 0.21 light-years, but in the next 300,000 years it is expected to gradually shrink to just 4,100 astronomical units. It takes Proxima 547,000 years to orbit around the system's common mass center. Unlike its two larger neighbors, the Proxima Centauri system boasts 2 confirmed exoplanets, as well as at least 1 hypothetical object. Besides, studies of the star in the infrared allowed scientists to assume that there is a dust ring and probably a great number of small celestial objects, like asteroids or comets. The first planet in the system, Proxima Centauri b, was detected in 2016 by the radial velocities method. 4 years later, in 2020, it was confirmed by spectrographic studies with the help of the largest Earth-based telescope on our planet, VLT, the Very Large Telescope. According to the updates, the exoplanet lies 0.05 astronomical units away from its parent star, and it takes it roughly 11 Earth days to complete a full orbit. Estimates show that the planet's mass is 10 to 20% bigger than that of the Earth, and its radius measures about 1.3 times that of our planet. Mathematical modeling revealed that Proxima Centauri b gets about 1.5 times as little thermal energy from its star as does the Earth from the Sun. Its average temperature is 234 Kelvin, or 39 degrees Celsius below zero, which means that hypothetically there could be liquid water in some areas on the planet. As the celestial body is extremely close to its host star, however, it is likely to be tidally locked, so it faces the star with one and the same side. A dense atmosphere could compensate for sharp contrasts in temperatures, which are inevitable in such conditions, but just like any other red dwarfs, Proxima Centauri is often seen to eject stellar matter. Also, ionizing radiation flares are observed. It is assumed that such activity gradually destroys the atmosphere of the closest objects. A powerful magnetic field that could be encompassing Proxima Centauri b could offer some protection against the destructive process, but chances that there is any magnetic field there are thin. In the year 2020, another planet was confirmed to exist in the system. A space object dubbed Proxima Centauri c lies roughly 1.5 astronomical units away from the center of the system. Its orbital cycle is slightly over 5 years. As for the object's mass, it may be 6 to 8 times that of the Earth, but its radius hasn't been estimated at the time this video is posted. Depending on its size, meanwhile, the exoplanet will fall either in the category of mini-Neptunes or super-Earths. As Proxima Centauri c lies quite a big distance away from its parent star, its temperature is remarkably low, about 39 Kelvin or 234 degrees Celsius below zero. According to some observations, the planet may have a ring system whose radius is roughly 5 times that of Jupiter. Also, based on the latest data from VLT, a remarkably small exoplanet is expected to lie 0.029 astronomical units away from its parent star, whose mass is about 25% that of the Earth. If it does exist, and if this isn't another measurement error, a year on this planet lasts about 5 Earth days, and the surface temperature there could be 360 Kelvin or 87 degrees Celsius. Whether this space object is really there or not remains an open question, and additional confirmations are called for. Alpha Centauri has been listening to our radio signals for over 100 years now. But the 40 trillion kilometers of space vacuum between us are too overwhelming for us to cover at this point. It takes light over 4 years to get there, but for humans such speeds are still in the realm of fancy. Even today's swiftest state-of-the-art spacecraft would need tens of thousands of years to cover this distance. However, application of advanced technologies could theoretically greatly reduce travel time. Since the very dawn of space exploration, projects of a great number of spacecraft have been suggested that hypothetically would have been able to negotiate interstellar distances. Nevertheless, not a single one of them has been actually designed. Most of these would-be missions were forgotten, but one is still under active consideration. This is the Breakthrough Starshot program, which implies sending as many as 1,000 microprobes to Proxima Centauri as soon as in the first half of this century. They will not measure over a centimeter in size, and special thin and durable sails are planned to be created to aid the probes along. The sails will be blown out, as it were, by impulses of a highly powerful Earth-based laser. Estimates show that an interstellar probe like that is going to be leaving the solar system at a speed roughly 20% that of the speed of light, with the overall travel time around 20 years. After that, it will take another 5 years or so for the data collected by the mission to reach the Earth. Before we set out on a space journey beyond the boundaries of our system, we have to decide on the manner of selecting a planet that resembles the Earth most from thousands of candidates. What should be the parameters of this fascinating world, and what should we take into consideration first? It goes without saying that planets favorable for the genesis and sustenance of life have always posed considerable interest to scientists. However, it is no easy matter to single out suitable celestial bodies among a great number of those discovered by now. To have clear-cut selection criteria, scientists worked out the so-called Earth Similarity Index, or ESI for short. It is based on several principal parameters: a planet's radius, density, and average surface temperature. This combination makes it possible to calculate the object's mass, approximately estimate its chemical composition, gravitational level, whether or not there is an atmosphere, and if there is, analyze some of its characteristics. It also helps establish if there is liquid water on the planet's surface and other information. The standard of this index is the Earth, with its parameters assumed as ideal and its ESI equaling 1. Based on the Earth Similarity Index, all the objects known to us conventionally fall into 3 categories. The first one is objects whose ESI is under 0.5. These are for the most part gas and ice giants, as well as extremely hot or on the contrary cold objects. This is the category most of the solar system planets and satellites fall into. It takes just one characteristic to greatly exceed the maximum permissible values for a celestial object to be unfavorable for the genesis and sustenance of life. Let's take Venus, for instance. The radius and mass of this celestial body are very close to those of the Earth. However, due to its close proximity to the Sun and a dense atmosphere, its surface temperature is extremely high. That is why, in spite of a close similarity to the Earth on the face of it, Venus's ESI is not high, at just 0.44. Of course, there being any life on its surface is totally out of the question. Celestial objects whose ESI is within 0.5 to 0.7 fall into the second category. These objects resemble our home planet noticeably more. They're mostly rocky worlds with relatively moderate temperatures, but it can also be ocean planets and even some large satellites. Incidentally, a high Earth similarity index per se does not warrant favorable conditions for life. For example, quite often low-mass planets are incapable of retaining a dense enough atmosphere, while their magnetic field is too weak to protect the surface from lethally dangerous radiation. Other celestial bodies yet may happen to be located too close to their parent star and so get tidally locked. Of course, all these factors greatly reduce the chances of life's genesis and sustenance. As for the third category, it contains celestial bodies with a high ESI, that is over 0.7. All of these planets are beyond the solar system. According to estimates, the size of these worlds and the conditions on their surfaces are potentially close to those of the Earth. Among these planets, there is one which resembles ours most, and it lies just 12.5 light-years away from the Earth. This amazing world orbits Teegarden star, a small red dwarf discovered in 2003. This star is 1,370 times dimmer than the Sun. This means that it cannot be observed with the naked eye, even though it lies quite close to the Earth. The mass of this tiny star is roughly 9% that of the Sun, and its radius is about 5% bigger than that of Jupiter. Gravitational forces are barely strong enough to maintain the thermonuclear reaction in the star's interior. That is why the surface temperature is just 2,900 Kelvin, or roughly 2,630 degrees Celsius. As is the case for all red dwarfs, Teegarden star's habitable zone is comparatively narrow and located very close to it. Back in 2019, 2 exoplanets were detected in its system after continuous observations of the star's proper motion. Interestingly, one of them lies beyond the star's habitable zone and the other within. The outer planet, dubbed Teegarden C, follows an almost ideal circular orbit around the system's center. With the orbit's radius 0.045 astronomical units, it is completed every 11.5 days. It is presumably a rocky celestial body with a mass 11% bigger than that of the Earth. Its radius is estimated to be approximately 3.5% bigger than that of our planet. Unfortunately, conditions on Teegarden C's surface are far from hospitable. Due to the low luminosity of its parent star, the object enjoys 63% less energy than what the Earth receives from the Sun. As a result, the planet's surface temperature is gauged at 47 degrees Celsius below zero on average, which is too low for life sustenance, at least in the forms we know it. Still, the chance of there being vast oceans of salty water concealed under a thick layer of ice on Teegarden C, as is the case with Jupiter's satellites for instance, shouldn't be ruled out. As for the inner planet, it is dubbed Teegarden B. It is actually this planet that is the most Earth-like object of all those discovered to date. Its ESI is 0.95, which is just 0.05 less than the standard ideal value of our Earth. This celestial body lies 0.025 astronomical units away from its star, and it takes it roughly 5 days to complete a full orbit around it. By following a practically circular orbit, the exoplanet is constantly in its star's habitable zone, and it receives 15% more radiation from it than the Earth from the Sun. According to some estimates, Teegarden B's mass is just 5% more than that of our planet. As for its radius, it differs from that of the Earth by a minuscule ratio, which means that the gravitation value is also quite close to what we're used to on our home planet. This makes it logical to assume that the inner makeup of the exoplanet is highly likely to be similar to that of the Earth. There is a massive metallic core coated in a thick layer of molten silicate mantle reckoned to be at the center of the planet. The celestial object's outer part is covered with a relatively thin crust of solidified rocks. Mathematical modeling shows that the average temperature of Teegarden B is 28 degrees Celsius, which is 14 degrees more than that of the Earth. This means that conditions on its surface allow the planet to have and retain an ocean of liquid water, and the planet's temperature profile is potentially favorable for most microorganisms. Even though Teegarden B is quite massive, and is capable of retaining a comparatively dense atmosphere, the radial velocities method, which is used for exoplanets detection, is quite inadequate for obtaining any information about the atmosphere's composition. But it should be borne in mind that a planet's temperature profile directly depends on its atmosphere's composition. For example, a dense atmosphere with a high percentage of methane and carbon dioxide will cause a strong greenhouse effect. Dense clouds of water vapor, meanwhile, will on the contrary reflect sun rays, which reduces temperatures. We should also remember that no matter how optimistic the parameters of this fascinating celestial body might appear, it is not entirely flawless. Being in close proximity to its parent star, it seems that Teegarden b is always facing it with one and the same side, which causes sharp temperature differences between the day side and the shadow side. As I've already mentioned, Teegarden's star is a red dwarf, and this class demonstrates a tendency to suddenly flare up. The amplitude of fluctuations in its luminosity may reach 30%, which greatly affects the planets located close by. Still, the chances of Teegarden b's capability of sustaining life are high. Biological creatures often demonstrate incredible viability, and their ability to adapt can't but amaze. For example, the ocean could serve as protection against lethal radiation and sharp temperature fluctuations. Its upper layer is potentially capable of absorbing cosmic radiation, while its currents could dissipate temperature contrasts. For all we know, as time goes by, primitive organisms might evolve in the warm depths saturated with energy and microelements. Just a tiny chance is sometimes enough for life to develop into something bigger. Every year, astronomers announce the discovery of several dozen new exoplanets. The number of new worlds discovered in the past 20 years is hundreds of times bigger than in the entire history of observations. Thanks to technological advancement, scientists constantly obtain new instruments for our knowledge expansion, and one can't help feeling that very soon, the long-awaited seeds of some alien life will be detected in some corner of the universe. By galactic standards, the area of space on the outer edge of the solar system is considered to be sparsely populated by both stars and other space objects. Still, approximately 50 stellar systems are known to be located within the radius of 15 light-years from the Earth. Some of them are single stars, while others contain 2 components and more, which is why the total number of stars in this area reaches 65. Many of them have exoplanets and protoplanetary disks made up of gas and dust, where celestial body formation processes are still in progress. In order to analyze this great variety, we'll have to map out the environs. As we slowly recede from our home planet, we will cover dozens of light-years of space and visit quite a few remote worlds. It is time to set out to the stars. Having traveled 6 light-years away from the Sun, we will reach our first stop, a small red dwarf, designation GJ699, also known as Barnard's star. It is remarkable for its incredible travel speed across the sky, and also for the fact that it's capable of crossing the lunar disk in the course of 180 years. This is due not only to its close proximity to us, but also to its great proper motion. Barnard's star is moving towards the solar system at a speed of slightly over 100 km per second and is going to become our closest star in about 10,000 years. By then, the distance between Barnard's star and our Sun will be just 3.8 light-years. But the red dwarf is so dim that it will not be visible even at such a small distance, and it will be possible to observe it only through optical devices. The star's mass is just 17% that of the Sun, and its radius is 6 times as small as that of our star. Just like all red dwarfs, Barnard's star is quite cool, with a surface temperature just 3,134 Kelvin, or slightly under 2,900 degrees Celsius. With these characteristics taken into account, It isn't surprising that the object's luminosity is 2,300 times lower than that of our parent star. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence for the presence of an exoplanet nearby. The calculations show it to be a cold super-Earth with a mass of not less than 3.2 times that of the Earth. The planet, named GJ699b, is located about 0.4 astronomical units from the center of the system and takes 233 days to complete a full orbit around its parent star. Unfortunately, the exoplanet follows an orbit that does not lie between the Earth and its parent star, so it's hardly feasible to carry out spectral analysis of the object. Still, mathematical modeling may give us some insights into what it's like. As Barnard's star is very dim, its planetary companion receives 50 times less energy than does the Earth from the Sun. That is why the temperature on the celestial body's surface is extremely low, just 105 Kelvin or 168 degrees Celsius below zero. However, it cannot be ruled out that tidal disturbances or radioactive decay may have released enough energy in the planet's interior to form a warm subsurface ocean. If that is the case, the potential life in its depths would have had ample time to gradually develop. For among the known stars, Barnard's star appears to be one of the oldest. According to estimates, its age is over 10 billion years, which is only a fraction of the expected lifespan of a star. As it is located quite close and is moving in a favorable direction, Barnard's star is one of the highest priority objects for a potential interstellar flight. Time will show if spacecraft launched from Earth will ever reach it. Meanwhile, on the other side of the Sun, there lies the almost exact opposite of the dim red dwarf. Of course, we're talking about Sirius, the brightest star in the night sky, which is 8.6 light-years away from our planet. From Earth, the star appears to be a single light source, but close inspection revealed that it is not a single object, but a binary star. The two components of the system are currently at their maximum distance from each other, about 30 astronomical units. The main star, also called Sirius A, is a bright blue and white star with a mass 2 times that of the Sun. At the same time, it is about 70% larger in diameter, and its surface temperature reaches 10,000 Kelvin. Because of this, Sirius A emits 25 times more energy than our Sun. The second object, known as Sirius B, is barely visible against the background of its bright and massive companion. It is a white dwarf with a radius of about 6,000 kilometers and a mass very close to that of the Sun. Like all stars of this type, its surface temperature is extremely high, reaching 25,000 Kelvin. However, due to its small size, this white dwarf is about 1,000 times dimmer than its stellar companion. After long and persistent research, no signs of planets have been found in the vicinity of Sirius. The reason for this may lie in the comparatively young age of the stellar system, or else the special position of the ecliptic plane. Because of this, the hypothetical exoplanets do not pass between the light source and the Earth, and therefore cannot be detected by the transit method. Another hypothesis claims that Sirius B exhausted its stellar fuel supply roughly 120 million years ago and transformed into a red giant. Soon afterwards, it shed its outer layers, turning into a compact and very hot white dwarf. As a result, the protoplanetary gas and dust disk enveloping the young stellar system at the time was destroyed by this explosion, its remnants scattered into the space around, denying the forming planets any chance of survival. Currently, both components of the system are moving around a common mass center in moderately elongated orbits, completing one every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, becoming brighter and more visible in the night sky. The minimum distance between us will be about 7.5 light-years, after which the system will start to slowly drift away from us. Things will go on like this for about another 660 million years, after which Sirius A will meet the same fate as its companion. For a brief moment, a massive flare will boost its luminosity by a factor of thousands, but within a few months, the star will fade completely, vanishing from the sky forever. Leaving the vicinity of Sirius, permeated by lethal ultraviolet radiation and stellar wind, we will perform a maneuver near the solar system to reach a small star 14 light-years from the Earth. It is designated differently in different catalogs, and one of its names is Wolf 1061. The star is a red dwarf with a radius of about 30% that of the Sun. Its mass is about 4 times smaller than that of our star, and its surface temperature is 3272 Kelvin, or about 3000 degrees Celsius. Like all objects in its class, Wolf 1061 is extremely dim. Its luminosity is only 0.14% that of the Sun, so the star is not visible to the naked eye from Earth. However, this red dwarf has one of the most abundant and diverse planetary environments of any stellar system near us. As many as 3 exoplanets have been discovered in its vicinity, all of them rocky and similar in composition to Earth. But still, conditions on each of the 3 celestial bodies differ considerably. The first and closest exoplanet to the parent star is called Wolf 1061b. It is located 0.038 astronomical units from the center of the system and completes a full orbit around it roughly every 5 days. The object has a mass in the range of 1.5 to 2 Earths and a radius 20% greater than that of our planet. It is likely that the celestial body is tidally locked and faces its star with one side at all times. For this reason, the temperature on the day side of the planet is extremely high, and the flares and stellar winds of the star so close to it virtually rule out any chance of there being an atmosphere. All these factors make the exoplanet completely unsuitable for the genesis and support of life. The second object in the system, Wolf 1061c, is located 0.089 astronomical units from its star and completes a full orbit around it roughly every 18 days. Thus, it is within the habitable zone of the star and can be considered a potentially habitable celestial body. Wolf 1061c is about 3 to 4 times more massive than our planet and belongs to the class of super-Earths. Observations show that its radius is about 1.6 times that of Earth, while the gravity on its surface is calculated to be 60% higher than what we're used to. The exoplanet receives noticeably less energy from its star than the Earth does from the Sun, so its temperature of equilibrium is much lower. It is 223 Kelvin, or about 50 degrees Celsius below zero, which is slightly higher than on Mars. Nevertheless, given variations in temperature during the day and from season to season, liquid water may well exist on the surface of the celestial body. With a dense atmosphere with a pronounced greenhouse effect, this probability is even higher, and conditions on the planet could approach favorable ones. Of all the potentially habitable exoplanets known to date, Wolf 1061c is one of the closest, ranking 5th on the list. The third object in the system is called Wolf 1061d. It follows a clearly elongated orbit, with the distance between the parent star and the aphelium reaching 0.73 astronomical units. As for the perihelion, it lies much closer to the system's center, just 0.21 astronomical units away. It takes the celestial object about 217 Earth days to complete a full year rotation. The mass of Wolf 1061d is calculated to be roughly 7.7 times that of our Earth. If this celestial body turns out to be a rocky object, its radius is supposed to measure about 1.7 times that of the Earth. If, on the other hand, this planet falls in the category of mini-Neptunes with a thick multilayer atmosphere, its diameter is supposed to be not less than 2.2 times that of our planet. In spite of a comparatively high eccentricity of its orbit, Wolf 1061d never enters its star's habitable zone. The celestial body is likely to be completely unsuitable for supporting life, but may pose a great scientific interest in terms of planetary evolution. This system is one of top priority destinations for future explorations, and it is highly probable that there are new discoveries to be soon made in it. In addition to everything else, the star Wolf 1061 is also remarkable for its position, which is virtually at the very edge of the so-called local interstellar cloud. It is an area in space filled with hot but extremely rarefied hydrogen. Its temperature measures about 7,000 Kelvin, and on average there is just 0.3 of an atom to be found in 1 cubic centimeter of space here. It is about twice as little as the average value in the Milky Way. The solar system has been moving through the local cloud for the past 10,000 years. Its average diameter is about 30 light-years, but our system is almost at its very edge. Alpha Centauri, for example, is already in the neighboring so-called G-cloud. We, on the other hand, will spend about another 2,000 years within our cloud, after which we will enter an even thinner and hotter region. The local interstellar cloud was formed by the collision of two giant bubbles of hot cosmic gas. It has a momentum of its own, which is perpendicular to the direction of the solar system's motion, and also has a magnetic field and radiation. Fortunately, despite the high energy of the interstellar gas particles that make up the cloud, there is no threat to organisms on Earth. The solar wind is a reliable protection against cosmic hydrogen, and the Earth's dense atmosphere takes the hit of particles that do break through the heliosphere. Still, traces of the isotope Iron-60, also called interstellar iron, have been found in the ice of Antarctica. It is thought to have arrived to Earth from no other place but the local interstellar cloud. As we continue our journey through space, we will soon get to a rather unusual star called AP Columbae, located 27.4 light-years away from Earth. First and foremost, it draws our attention because it was born just 40 million years ago, when the dinosaurs would have long since died out on our planet. What is even more striking is that its birth took place in a completely different region of the galaxy, 450 light-years from the object's present position. Young stars usually remain close to their stellar nursery for quite a long period of time, up to several 100 million years. If you analyze the movement of AP Columbae, however, you will find that it probably previously belonged to the open cluster IC2391. The cluster has about 30 stars, united by a common origin and direction of movement. But a few million years ago, one of them exploded, shattering the delicate equilibrium of a multitude of cosmic bodies. This catastrophe gave the young star an additional momentum that swiftly expelled it from its birthplace. A very small red dwarf with a mass just 13% that of the Sun, this star emits 4 times more energy than any other known celestial body with the same parameters. In addition, its radius is twice as large as calculated based on the modern stellar structure theory. Strangely enough, another unusual feature of the star has helped to provide answers to these riddles. According to spectral analysis of its radiation, the stellar matter of AP Columbae contains an abnormally large amount of lithium. Normally, this element is found in abundance in protostellar clumps, but it burns out completely after the start of a thermonuclear reaction. This means that the star is very young and at the very beginning of its formation, not even in the main sequence phase yet. As a consequence, AP Columbae is unstable and explosive in nature. It is prone to violent outbursts and stellar matter ejections, during which its luminosity may increase by up to 10 times for a short while. Such events would normally threaten exoplanets nearby, stripping off their atmosphere and sterilizing their surface with ultraviolet radiation. As it is, observations show that there are no large space objects within 4.5 astronomical units of this star. In all likelihood, it is too young for the formation of fully fledged planets. Nevertheless, it is a unique cosmic body, very important for understanding early evolutionary stages of stars. As we've seen, not every star has a planetary system, so our next stop is near the orange dwarf Gliese 370, 37 light-years from Earth. In 2011, a single exoplanet was discovered near it, designated Gliese 370b. The object was discovered with the use of the radial velocity method and has a mass of 3 to 4 Earths. According to current understanding of the formation of celestial bodies, the discovered world is most likely a rocky planet, with a radius about 30% larger than the Earth's. Under such conditions, the gravity on its surface may be at least 40% higher than what we're used to. Gliese 370b is located at a distance of 0.26 astronomical units from its parent star and completes an annual rotation in 54.4 Earth days. Thus, the exoplanet is in the habitable zone of its star. If the albedo value of its surface is close to that of the Earth, then the average temperature of the celestial body should be about 25 degrees Celsius, which is a few degrees higher than on our Earth. The fact that an exoplanet is located quite far from its parent star suggests that it is not tidally locked and has its own diurnal cycle. This contributes to an evener distribution of heat over the surface of the celestial body, which as a consequence may create a milder climate. A moderately high gravity should smooth out the planet's terrain, which combined with an abundance of liquid water may cause vast seas to form, both warm and shallow. Such places have traditionally been considered the most comfortable for the genesis and support of life. At the time of its discovery, Gliese 370b was considered one of the most favorable exoplanets for potential biological life. However, more recent research has suggested that conditions on its surface are somewhat less attractive than previously thought. In particular, the atmosphere of the celestial body may be too dense and have a pronounced greenhouse effect. Still, even according to the most pessimistic predictions, the average temperature on the surface of the object does not exceed 78 degrees Celsius, which corresponds to a temperature range of about 30 to 100 degrees Celsius. Given that our planet's climate was about the same during the Archean period, Gliese 370b remains a very promising exoplanet for the search for extraterrestrial life, which means that its exploration must continue. If we stop and look around for a while, we will find that we have already traveled more than 50 light-years away from our solar system. There are over 1,000 stars within its radius, most of them single stars. Others are binary stars or even groups of stars. The most striking example is Castor, a complex and surprising system of as many as 6 components. This stellar system is located 50 light-years away from Earth and is visible to the naked eye as a single source of light. As the second brightest object in the constellation Gemini and the 23rd brightest in the night sky in general, Castor has been known to humans since ancient times. As the system has as many as 6 components, it has a rather complex structure. The 2 brightest of these, Castor A and B, are bluish-white Sirius-like stars, each with a red dwarf companion nearby. The distance between the mass centers of these binaries is about 110 astronomical units, and it takes them 445 years to complete a full orbit. About 600 astronomical units from Castor A and B, there is another compact binary system, consisting of a pair of almost identical red dwarfs. Each has a mass of about 0.6 times that of the Sun and has a surface temperature of about 3,900 Kelvin. The 2 stars are so close together that they take less than 20 hours to complete a rotation. They move around the system's common mass center following a very oblong elliptical orbit with an orbital period of about 14,000 years. So far, no confirmed exoplanets have been found in the Castor system. But if they do exist, they're most likely to be located here, near the faintest component of the system. In 2018, for example, astronomers detected variations in the orbital period of Castor C, which implies there may be a brown dwarf nearby, about 49 times more massive than Jupiter. According to calculations, it is located 14 astronomical units from the parent star and completes a full orbit around it every 54 years. It is possible that, like many red dwarfs, Castor C has rocky exoplanets close by. In this case, the skyline of such a hypothetical object must present a truly incredible spectacle. On one side, a considerable part of it is occupied by two crimson stars circling the sky without stopping, while on the other side, the eternal twilight is diffused by the light of a pair of stars, either of them hundreds of times brighter than the Earth's moon. Whether this is actually the case cannot yet be verified at this point. Although the stars we have visited are great distances apart, they are all within a single structure stretching for the total of about 300 light-years. This is called the local bubble and contains not only thousands of stars, but also several large structures, including the local interstellar cloud. The local bubble was formed by successive explosions of several supernovae that occurred between 10 and 15 million years ago. It is a giant cloud of interstellar gas heated to 1 million Kelvin. Because of its high temperature, the gas tends to expand, so its density is about 10 times lower than the galactic average. In addition, the hot ionized hydrogen constantly emits X-rays. Fortunately, the magnetic fields of the Sun and the Earth, as well as the atmosphere of the planet, successfully protect us from the harmful radiation. The local bubble is bordered by other similar formations. For example, slightly away from the direction of the solar system's motion is the so-called Bubble 1, formed by supernova explosions in the vicinity of Antares. This giant cosmic structure has been actively interacting with our bubble for a long time, which has caused the formation of tremendous compactions located at the region at the edge. The center of the neighboring bubble is about 500 light-years from us, and the solar system will reach its margins in a few tens of millions of years. Clouds of scorching hot gas and open clusters, giant nebulae and stellar streams. All these majestic cosmic structures add up to a single system called galaxies. In turn, they combine to form galactic filaments, giant streams and walls stretching for billions of light-years. This forms the large-scale structure of the universe, with countless different stars and worlds lurking in its depths. Who knows what we're eventually to find among them? The year 2003. As the starry sky was being routinely observed, a small yellow dwarf was detected in the Phoenix constellation. It was later to be dubbed WASP 96. The year 2013. The Super WASP orbital telescope detected an extremely rarefied gas giant in the immediate vicinity of the star. A preliminary spectral analysis of its atmosphere revealed that it was remarkably transparent and practically devoid of any water vapor. The year 2022. Analysis of the object's atmosphere was conducted again, this time with the help of the new generation orbital telescope James Webb, which offered an unprecedented accuracy. Scientists were taken aback. If the new data were to be believed, the exoplanet was supposed to be shrouded in thick layers of clouds, which was the exact opposite of what the previous observations had revealed. Thus, the data from the James Webb was in conflict with the earlier estimates. and the degree of our understanding of the universe was questioned yet again. So, what is this amazing telescope like? And what has it seen in the depths of space so far? Let's take a closer look at it. The history of the largest modern orbital telescope began back in 1996. Its development and modernization took as long as 25 years, after which the spacecraft left our planet and set out on its journey through space. It took James Webb a month to reach its destination point, located 1.5 million kilometers from our planet. Because the telescope is equipped with high-precision infrared sensors, it can see the dimmest and most distant space objects hidden in the depths of the universe. However, this unmatched sensitivity also has a downside. The intense radiation from the Earth, the Moon and the Sun interferes with the faint signals of distant stars and exoplanets. Therefore, in order to counteract this effect, the super-sensitive instruments were covered with a multi-layer heat-reflecting screen. The observatory itself had to be moved away from large celestial bodies and be located near the so-called second Lagrange point in the shadow of our planet. Still, the obtained results were absolutely worth all the effort, because James Webb helped us make quite a number of amazing discoveries pretty much from the very first days of its operation. With some of them quite expected, others, on the other hand, prompted additional questions. One of the studies with a paradoxical outcome was the spectral analysis of WASP-96b, a glowing exoplanet of extremely low density. It is located 0.045 astronomical units from its parent star and completes a full orbit around it in just 3.5 days. According to calculations, the mass of the celestial body is half the mass of Jupiter, and its diameter is 20% more than that of Jupiter. Because of the extreme proximity to the star, the temperature of the object's outer layers is quite high and reaches 1285 Kelvin, or just over 1000 degrees Celsius. Exoplanets of this type fall in the category of hot Jupiters and are distinguished by large losses of atmosphere due to stellar wind. Earlier measurements showed very clear lines of sodium in the atmosphere of WASP-96b, which was interpreted by the researchers as a sign of an unusually clean and cloudless atmosphere. The fact is that according to the available models of the structure of gas giants, this element can exist only in the planet's interior. As we can see traces of it, it means that the upper regions of the celestial body's atmosphere practically do not absorb light. It was assumed that thanks to this, the ultra-sensitive detectors of James Webb could look into the deepest layers of the exoplanet. However, the information obtained by the telescope turned out to be radically different. The outer layers of the gas giant contain great amounts of water vapor. It condenses in the upper atmosphere and can form a large haze or thick clouds, reflecting some of the light shed on it. Because of this, the temperature of the lower layers of the object may differ significantly from the calculated values. Perhaps the accuracy of the earlier study was insufficient, or else some of the data was misinterpreted. It is also possible that we do not yet know of a certain factor that would allow us to combine the results to form a single correct picture. WASP-96b remains a mystery, which means it still needs to be studied in more detail. Of course, James Webb's discoveries do not end there. For example, 69 light-years away, there is an unusual system consisting of 3 brown dwarfs at once. These cosmic bodies are too big to be planets and at the same time too small to launch a stable thermonuclear reaction in their interior. Brown dwarfs are usually difficult to detect, as the radiation of their surface is extremely low. But James Webb sees the universe primarily in infrared, which makes it easy to distinguish objects that are virtually invisible in the optical range. The 2 largest components of the system are very similar in their characteristics and are located quite close to each other. The distance between them is about 2 astronomical units, and their total mass is slightly more than 100 times that of Jupiter. The temperature of both objects is relatively high, reaching 2600 Kelvin or slightly over 2300 degrees Celsius. The third component of the system is at a much greater distance, about 100 astronomical units from the center. Its mass is between 14 and 23 Jupiter masses, and its radius is 20% more than that of Jupiter. Also, this brown dwarf is about twice as cold as its more massive companions. Observations revealed that the temperature of its outer layers is 1240 Kelvin or slightly below 1000 degrees Celsius. Nevertheless, the celestial body is considerably warmer than the gas giants in our system, especially given the absence of a star that would give it heat. It was surprising to find that the outer layers of this brown dwarf contain not only the usual components such as water, methane or carbon dioxide, but also minute particles of various silicon compounds. The simplest of these is quartz, but more complex substances have also been detected. These are thought to be concentrated in the atmosphere of the celestial body in the form of vast clouds. The existence of such clusters had previously been predicted from theoretical considerations, because silicon, being a product of stellar thermonuclear reactions, is quite widespread in the universe. Still, until recently, observations have not been able to confirm this hypothesis. It is thought that about 140 million years ago, there was a single gas dust cloud in the system's place, which later split into 3 independent clumps. This event may have been caused by the gravitational influence of a massive celestial body that passed close to the protostellar nebula. Remarkably, if the separation had not occurred, the total mass of the formed object would have been enough to start a self-sustaining thermonuclear reaction. In this case, instead of 3 brown dwarfs, we might have been observing a single tiny star. Incidentally, the James Webb equipment is capable of observing not only single objects tucked away in the depths of space, but tremendous space structures as well, that stretch for hundreds of light years. One of them is the Carina Nebula, which is one of the largest stellar nurseries in our galaxy. This bright and vast cluster is located about 8,500 light-years from the Earth and has a mass of up to 900,000 suns. It contains not only giant clouds of interstellar gas and dust, but also thousands of stars, from the smallest ones to the most gigantic. This is where 2 of the Milky Way's brightest objects are located: Eta Carinae and WR25. The luminosity of each is several million times greater than that of the Sun. Unique objects like that certainly attract astronomers' attention. Besides, James Webb's infrared cameras are able to pick out great numbers of stars in the dusty haze, which were previously unknown to us. The point is that it is in this area in space that hundreds of young stars are constantly getting born. According to modern concepts, new stars are formed by gravitational forces that compress and heat up clouds of cosmic dust. During its evolutionary process, a protostar goes through several stages until finally a thermonuclear reaction kicks in its interior. This theory has been confirmed by multiple observations, but many details of this long and complex process currently remain understudied. The formation of a new star sometimes takes millions of years, but astronomers don't need that long to observe it. Thanks to James Webb's infrared sensors, thousands of protostars and young stars at various stages of evolution have been detected in the Carina Nebula. It is important to note that all these objects formed within the same gas cloud, which means that they are very similar in terms of composition and age. By observing them, researchers can fully trace the process of star formation and better understand what forces are involved. Some phases of this process, predicted only in theory, take hours or days, and with James Webb, the chance of capturing them is greatly enhanced. For all we know, we may soon be able to admire a photo of a young star flaring up thousands of light years from the Sun. Meanwhile, an 18-section mirror 6.5 meters in diameter and an onboard array of high-accuracy instruments allow James Webb to capture light from objects much further away, at the very edge of the visible universe. They are more than 13 billion years old, giving us a glimpse of the earliest times immediately after the hypothetical Big Bang. However, even James Webb would not have been able to see their luminescence but for one unique coincidence. The phenomenon of gravitational lensing has long been known to scientists. This physical phenomenon helps us to better see into the depths of the universe. And this is how it works. A powerful gravity generated by a massive body focuses and amplifies the light from a source behind it. Such an effect can be produced only on condition that a great many factors happily combine, so it is not surprising that it is one of the rarest phenomena in the universe. It is all the more surprising that while observing the galaxy cluster SMACS 0723, located about 4 billion light-years from the Earth, James Webb captured light of a space object passing through gravitational lenses as many as 3 times. In total, the radiation was amplified about 20 times, without which astronomers would hardly have been able to distinguish it from background noise. The object is thought to be a distant and very old galaxy, whose age is estimated to be 13 billion years. About 10 other star clusters have also been detected, which are thought to have originated between 200 and 700 million years after the genesis of the universe. According to some observations, they have a complex structure which takes tens of millions of years to form. This discovery will allow scientists to develop the existing ideas about the early stages of the universe's evolution and may even prompt to question its age. Unfortunately, we still know very little about such remote times, and James Webb will surely help us learn more about them. The universe offers some truly magnificent and mesmerizing sights, and it is hardly possible for the human mind to fully appreciate its scale. What we observe is separate pieces of this enormous jigsaw puzzle scattered in time and space. Eventually, we might get all these pieces in place once, and who knows what the picture will look like.